All right, so this is group five, comprised of three persons, Ade, Mohammed, and Harris. We examined the traffic data provided by Ontario's Ministry of Transportation. This traffic data was obtained at different survey stations across the province, and details the volume of single unit trucks, multi-unit trucks, and auto and passenger vehicles over different hours in a week. So it's a week of data. The data set itself contains about 17,000 records and 13 attributes. We answered all of the questions detailed here and went beyond in some ways to shed more light on the available data. So the sections in this Jupyter notebook show that we analyzed the data going component by component. That is, we looked at the stations, the highways, directions of traffic, regions, and days and hours. At different points, of course, we combined multiple components and looked at how one of the components was related to the other. So under data preparation, we did the customary imports, pandas, numpy, matplotlib, and seaborn. Read the data into pandas here in this cell, and saw that most of the attributes had already the correct data types. So one thing also is that the data has no null values, which is a good thing. That means it was clean. Using the describe function here, we show that the data is heavily skewed to the right. The mean of all the numeric values is higher than the median or the 50th percentile, confirming that the respective numeric columns are skewed to the right. But how much is this skewness? It seems to be a lot, because the maximum values here in all of the numeric variables are all orders of magnitude higher than the 75th percentile. We'll see later in the histograms which actually confirmed this. So we also found 33 unique highway values, 104 unique station values, and 5 unique MTU values. So here in the histogram here shows the skewness of each of the volume of vehicle types provided in the data set. So we plotted this on a first set grid to enable easy comparison. So to be able to see this distribution better, it was important to transform it. So using a log transformation here in this cell, we are able to actually see the different distributions and compare them. We would not have been able to see the differences or the similarities in the distribution in the earlier histogram. So we could see here that the total vehicles histogram looks pretty similar to the histogram of auto, suggesting perhaps that the sum of all the different vehicle traffic has more of auto and passenger vehicles in it than it does of truck traffic. Perhaps this means there are more auto and passenger vehicles in the province. Also, the distribution of multi seems closer to that of total trucks than it does to the distribution of single. So maybe then there are more multi-trucks overall than there are single trucks. But we'll see more details about this in the later cells. So in the next cell, we attempted to check if there's any significant difference in the distributions of the different vehicle types. So we used the Kruskal-Wallis test to do this, since the distributions are not normal. And the p-value came out really low, confirming that the distributions are indeed all different. So next are the box plots here, which confirm our earlier suspicion that there could be outliers. So here, on the box plots on the right. So next we look at the box plots, and the box plots here to the right do not have the outliers, but the box plots to the left have got the outliers. So here we confirm our earlier suspicion that there could be outliers in the data set, but since all the data is actually valid, we will be leaving these outliers in place. So now we examine the data by stations. Which station has the biggest traffic? It looks like they are stations 115, 116, and 140. Combined, they make up close to 30% of the traffic experienced in the province. The bar plot here shows that there are a few stations reporting really high traffic compared to the many stations on the other end reporting low traffic. But where are these really high traffic stations, 115, 116, and 140? We'll see more information about these stations later. First, we look at which vehicle types contribute most to these heavy traffic. are these stations. On this bar plot, we see it's mostly auto, that's auto and passenger vehicles. Clearly, there is some bit of multi trucks, but it's they are rather insignificant compared to auto vehicles. Next, we examine the correlation of traffic among the different stations. How does traffic change from one station to the other? So we generated a huge 104 by 104 matrix showing the pairwise correlation between the different stations. So on average, the traffic correlation looks above 700%. This means traffic rises just about the same time at different stations and settles just about the same time. So their signatures all look the same. However, though the signatures may look the same, the respective strengths are actually different, as this next plot here shows. So here, all the plots have been done to the same scale. Stations 18 and 20 here have little traffic, while stations 16 and 21 have rather high traffic. This also allows us to observe a curious consistent peak at station 21, and investigating a little more, we find that it's repetitive and happens every afternoon on Highway 400, located around King Road and Kettleby Road, north of Vaughan. So this is where it's located, as we can see from the map generated using Folium, and it appears to be the daily traffic homeward from downtown Toronto. So using Folium, we're able to import many more maps from OpenStreetMap, which is open source, and examine some of these locations. So next, we examined the highways. Our earlier analysis showed that station 115 has the biggest traffic. This station is located on Highway 401, as we can see here. Most of these stations, which cover Highway 401, report intense traffic, as we can see in this next plot here. So Highway 401 does seem to be the one with the most traffic in the province, and 115, that station 115 in particular, is on Keele Street, as we can see here, and 116 on the other hand monitors the eastbound traffic on the same street. So 139 on the other hand, which also has Highway 401, which also captures Highway 401, is close to the major airport around Mississauga. So these are pretty intense locations. So little wonder the traffic on Highway 401 seems pretty high. So when we sort later by highway to determine, so when we sort by highway and arrange the results in decreasing order of mean traffic count, we confirm again that Highway 401, Queen Elizabeth Way, King Edward Avenue, and Highway 400 have some of the biggest traffic in the province. In fact, percentage-wise, as we can see in this next data frame, they contribute to more than 50% of the traffic in the province. But for the biggest highway itself, that's Highway 401, any insights? When we plotted the time curve, we found that the traffic on this highway begins around 5 a.m. in the morning and increases gently during the day, peaking around noon. On the last day of the week here, in this plot, it appears more cars stay on the road even towards the evening hours than they do on other days. Also, we found an interesting insight looking at the first and last day plots, and we see that there's a gentle slope for both days compared to a more aggressive slope on the other days of the week. So these days are Sundays and Saturdays, and clearly since less people hurry to work in the morning on these days, the slope is gentler than it is on the other days of the week. And this appears to be the same thing on Queen Elizabeth Way here in this plot here, and on King Edward Avenue here as well. But which vehicles contribute the biggest traffic per highway? Again, we find it's auto and passenger vehicles with multi-trucks coming in far second. But when you look at the percentage of trucks on the highway, we find that the biggest highways actually don't come into consideration here, as we can see in this data frame. For trucks, the biggest highways are clearly Highway 3, Highway 402 rather, Highway 405. at least when examined proportion-wise. When we look at the map on OpenStreetMap, we find that the two areas, the first two areas with the biggest truck traffic, are close to the border between the United States and Canada. So this makes sense. Commercial activities apparently causing a lot of truck traffic. So next, we look at the directions of traffic in the province. We find that more vehicles are moving towards the eastern direction, probably in the direction of the GTA, the province's financial district, from busy areas such as Hamilton and Mississauga, for example. The traffic towards the west comes a close second here, as you can see in this plot, and the lightest traffic apparently move north in the northern and southern directions. So next we examine the regions. These regions are the different regions the MTO has divided the province. So basically this is mainly for the MTO's convenience. So when we look at the regions, we find that the region with the highest traffic by a mile is the central region. This is no surprise. The central region is where Toronto is. So it makes sense that it should have the highest traffic count, though that's not surprising. What's surprising is that this region contributes nearly 70% of the traffic in the province. So that's quite substantial. In the plot, we find that the southwestern region comes second in terms of traffic count. Okay, so next we examine the data by days and hours, and when we do this, we find that the mean traffic per day does not seem to change much over different days. In fact, with the exception of little truck traffic on Sunday and Saturday, every other day seems fairly the same. But the hourly measure tells a different story. From the early morning hours to the evening hours, traffic seems quite sizable, though it appears that this is dominated by auto traffic. When we examine the percentage plot, however, we see that there is some good proportion of truck traffic in the early morning hours compared to the daytime hours. Apparently, most of the trucks move in the night. So next, we conducted some machine learning tasks to gain some additional insights. Here we used the K-means to cluster the available data into regions of different traffic sizes. First, we had to scale the data, however, since some have bigger weights than others. So we generated a cluster of 10. But before plotting the clustering results, we looked at the scatter plots. So we plotted total trucks against all other vehicle types and saw basically what most of the bar plots had shown us earlier, but this time a little more congregated. So the scatter plot of multi versus total trucks on the right side here has a slope close to 1 at lower values, suggesting that total trucks has more multi trucks in it than it does single trucks. But the auto versus total truck scatter plots shows more information. It shows firstly that there are more auto passenger vehicles in the province than there are other vehicles, and also that at areas of high auto density, the traffic of total trucks is pretty low. So all the points in the scatter plot are congregated at areas of low traffic, showing that there are many more areas with lower traffic in the province than there are areas of high traffic. So even though we may have been looking at areas of high traffic or highways with high traffic, we actually have more areas with lower traffic in the province. Now, that's more stations with lower traffic. But for these areas with high traffic, there are more autos causing this traffic than trucks. This is because most of the points in this scatter plot on this lower side are on the right side of the red line. So after applying K-means, we successfully clustered the data into 10 chunks, as seen here, from showing a spectrum of different traffic strengths. So we could use this to further classify the different areas into regions of varying traffic sizes should we need to do a classification task with newer data. Next, we used the fast Fourier transform to predict future traffic on the busiest highway, that's Highway 401, using the available data. So this algorithm, that's the FFT algorithm, appears to be very suitable for this type of time series, which follows an almost predictable pattern barring external factors. So here's the result of the prediction. The red line is the predicted value, following the original traffic data on the right, on the left, sorry. So next, we computed traffic probabilities using logistic regression. As a first step, we classed the data using the auto details. We classed the data into areas of high traffic and areas of low traffic, mainly by dividing the auto details into two. So using the training set, we created a model, and it looked pretty good. Came out with good p-values, at least for the single unit. And this showed that the odds of getting a high traffic increases by the exponential of x1 when we add single unit trucks to the highway. So this is quite a reasonable deduction. So we obtained an accuracy of 78% with the training set. So after passing the test set through the model, we obtained the different traffic probabilities here in this data frame for different highways. Again, Highway 401 remained the most problematic, but here we see the chances of getting stuck in traffic on this highway is quite high at 87%. Some of the other highways with lesser traffic reported lower probabilities, as you see here. So when we go to Google Maps to examine live traffic data, it did confirm some of the results we obtained. For instance, Highway 138 has a probability of 0.199 of getting stuck in traffic, and indeed it has very low traffic as seen here on Google Maps. So the interesting thing here is that all of the traffic live traffic data we examined, which reflect the current situation of traffic in the province, share similarities with the result of our analysis, which come from a data set that is more than 10 years old. So the similarity between our analysis and this most recent data suggested that not a lot has changed in the situation of traffic in the province over the past years. So in conclusion, we were able to derive some key insights from this data. Some of the biggest traffic in the province happen on Highway 401, Queen Elizabeth Way and King Edward Avenue. However, they do not have as much truck traffic as some of the other highways around the border. We also found, among other things, that passenger vehicle traffic constitutes the biggest traffic in the province. More passengers move in the province than do goods or trucks. So this could help correct the misconception that there are a lot of trucks in Ontario, when indeed there actually are more passenger vehicles than there are trucks. While most traffic happens towards the province's financial district of Toronto, other areas outside of Toronto, such as Mississauga, also experience significant traffic. Finally, we found that the highest traffic direction is eastbound, and this could be because of the location of Toronto, which is the province's financial district. So clustering offered an avenue to divide the data into a spectrum ranging from high traffic to minimal traffic based on the size of the traffic for any given hour. With this, we could label the data set into classes for future classification tasks. We also predicted some future traffic on Highway 401 using fast Fourier transform, which is very suitable for predicting such repetitive traffic patterns. Finally, we used logistic regression to examine traffic probabilities on different highways and confirmed this with live traffic from Google. One interesting observation following from this is that not much has changed in the nature of traffic in the province over the years. After conducting all these analyses, we have to admit that some of the conclusions derived are limited in reach or scope. Firstly, because the data has only a week of information, and secondly, because it's from more than 10 years ago. Were the data available over several months or years, or way more recent, we could certainly have derived better insights from it. Better insights reflecting current situations. The dataset also does not provide information on any construction or extraneous activities that may have been going on at the time the data was collected and which could have impacted traffic. So we are left to speculate on the cause of certain traffic patterns that we observed. Finally, the absence of GPS coordinates in the original data sets greatly limited what could have been achieved in terms of analysis. A good recommendation would be to include such data in future provisions of this data set. So that's it from Group 5. Thank you very much.